This is lecture 21. So last time we discussed some of the general concerns of what scheduling involves in the context of operating systems and what makes scheduling in operating systems different from other environments. So the idea of scheduling is quite broad. It's studied in many different disciplines and branches. Just in computer science, we study it in operating systems, in networks, where we are, where we are studying scheduling of messages called packets at switches, at routers, etc., scheduling of disks, and a whole lot of other particular application domains. It's not just in CS, in operations research, OR, as it's called. It is studied for product development and other many things that come about. So it's a very general topic. And what we are trying to understand is what does scheduling mean for operating systems, in particular for operating systems where we are trying to schedule not disks or some other devices, but processes running on CPUs. And what are the special traits that distinguish doing this compared to many other domains where the idea of scheduling comes into play? And there are other parts of scheduling that we are here not going to discuss. One is called real-time scheduling. That means that we have hard deadlines. We need to get something done by a certain time. And this is something that, for example, if you were to take the grad version, CS503, we would spend time on it and implement some parts of it, which is relevant for multimedia streaming. So you're streaming multimedia, and you need to make sure that video encoding, decoding, sending, receiving, all of that's under governance of the OS, and that's done in a timely manner. And there we have hard deadlines. So that's under real-time scheduling. So this is a very broad topic, and here we are trying to understand in our niche of using CPUs as our resource. So the resources can be diverse on which we perform scheduling. We want to know on CPUs where we have a bunch of processes that need to share the CPU or CPUs, what are the things that come into play that make OS scheduling different from other domains. And the key point that we established was that processes are of different types, and at two extremes there are those that really need a lot of CPU. We call them CPU bound, and at the other end we have processes, they do a lot of IO, and implicitly when they do IO, uh, IO bound, and when they do a lot of IO, implicitly we mean that they are likely to block, likely to block. So they make a system call, sleep, read, whatever the case might be, and those system calls block because what they need to do is not yet ready. So a message is not there, or a process wants to sleep. By definition, there's nothing for it to do until a future time when it wakes up. So to block means to give up the CPU, give up CPU voluntarily. So we saw already that when we have here user mode, kernel mode, and we talked about clock ringing, so this is the lower half, and we considered reaching the scheduler in two ways, 2 and 2 prime as we called it, and the 2 prime was when time slice was expanded. So all the time slice has been spent. Who detects that? The lower half. This guy detects it because it's the clock handling component of the OS. And when it detects that the current process has used up its time slice, then the lower half calls the scheduler, the guy here in between, so that the scheduler then can decide, should this guy continue to run or should this guy be kicked out, and another process is then context switched in. And so that was what we termed 2 prime. And so in this particular case, what can happen is that a process who wants to continue to run on the CPU is forcefully, is involuntarily being context switched out, because the OS decides you have used up your time slice, and it checks among all the ready processes, is there a process that's of higher or equal priority as this guy? And if the answer is yes, then by the scheduling policy, by the scheduling invariant, that the highest ready process should always occupy the CPU, this guy is going to be kicked out, and then the guy at the front of the ready list in Xenu would be context switched in. And that's the same for Xenu, Windows, Linux. It's a universal rule that schedulers in operating systems follow. So in that case, the key thing is that the process is being involuntarily context switched out. This is different from this IO bound guy who voluntarily gives up the CPU because it's making a blocking system call. In this particular case, this guy is likely to be a CPU bound guy because it ate up all of its time slice. That means it ran on the CPU for some time. And then it's the scheduler's action, so it's the kernel's action, that then determines that this guy should not be current anymore, and it context switches this process out. So it's done involuntarily. And so these guys, CPU bound guys, they tend to give up CPU involuntarily, and the IO bound guys, they tend to give up CPU voluntarily. That's their different nature. And when we are trying to achieve fairness, the reason why we are not satisfied with just doing round robin, which would be a decent approach, is because although this algorithm is very fair, so the mechanism, the algorithm is immensely fair, but it doesn't take into account the nature of the workload. So in computer science and in operating systems, the work that we need to do, which in this case is to manage processes. These are our apps. That's our workload. So in computer science, specifically in the case of operating systems, there's a special trait of the workload that we need to consider that distinguishes it from other scheduling domains. And in this workload, we are going to have this viewpoint of CPU-bound processes versus IO-bound processes, and of course in between hybrids, or a process that is CPU bound for a while, changes its property to being IO bound for a while, etc. So there can be lots of different cases. But these two endpoints are a useful framework to consider how to perform scheduling so that we achieve a better outcome than doing purely round robin. And the main thing that we can draw from all of this motivational background and discussion is that we want these IO bound guys, which by their very nature will take up much less CPU time than those CPU bound guys. We want to compensate these guys for the fact that they are inherently not going to tax the CPU much by doing something for them. And it turns out that these guys overall, not always, but overall tend to want or tend to benefit from having fast responses. Response. That is, responsiveness is an important performance criterion that these guys benefit from as a class of apps. And again, those are varied, but oftentimes interactive apps that tend to fall in this category, they want to have responsiveness. So if you're clicking on your mouse and you are now going to browse the web, then you don't want your mouse to be sluggish. You want there to be fast responsiveness. So if a process that's part of your browser app, if that guy has been context switched out and then suddenly you start to move your mouse, then you don't want that to take a long while before that process runs and then controls your mouse. As a toy example, you want that to be quick. And so the goal here for fairness is not just simplistic round robin fairness, which is a good start, but in operating systems, keeping in mind the nature of the workload, we are setting the bar, we are setting our target to be more ambitious. We are not satisfied with just doing this round robin. We are trying to make sure that these IO bound guys actually benefit by having better responsiveness. And that fits nicely with the overall nature of these apps, and that's the central tenet. That's been a central motivating factor of how in operating systems scheduling has been approached for placing processes on one or more CPUs. So that's our general background here. And we said that the basic idea is assign these IO bound guys. So assign IO bound processes higher priority vis-a-vis CPU bound guys. That is the basic idea. So a useful way to look at the overall approach that has dominated operating systems design in terms of process or scheduling is to look at a 2x2 table. So here's our 2x2 table. And what are we going to consider? So here we are going to say that we have a CPU bound process type and here an IO bound process type as a reference point. And what can we in scheduling, in OS scheduling, what are the things that we can control? What's under our control? One is priority. We know that already. So priority is a variable that we, as the kernel, can manage by giving some processes higher priority or smaller priority and changing that over time. The other main control variable we have seen already, it's time slice. We have a way of making the time slice to be larger or smaller for certain processes. We can make priority higher or smaller depending upon whether a process is deemed CPU bound or IO bound. So here is time slice. So the general idea is, so here we're trying to compare, relatively speaking, how are we going to set the priorities and the time slices when we consider two processes as examples, one which is IO bound, one which is CPU bound. So this is purely a relative comparison. So for priority first, we said we want to give the IO bound guys, all else being equal. Let me use a different color, black, high priority, high or higher compared to a CPU bound process. So here, let me say low. So this is relatively speaking. Then what about time slice? The CPU bound guys need CPU, so they benefit from having a large time slice. These IO bound guys, they don't need much CPU. So for them, having a small time slice is okay. So this table and these tendencies, these biases as shown here, that has been the general tendency and the general approach in coming up with how process scheduling is done in operating systems. So again, all else being equal, we want to assign IO bound guys higher priority vis-a-vis CPU bound guys. That's going to give, so this is going to give better responsiveness. Better responsiveness to IO bound guys. IO bound processes. So when an IO bound guy is blocking, but it becomes ready and it joins the other processes who are ready, by virtue of the fact that we gave this guy a high priority, if all of these ready processes, so these are all the ready processes, and suppose that many or all of them are CPU bound. Well, if they are CPU bound, then obviously if here is a process that was blocked sleeping, and now this IO bound process joins all these other ready guys from which the scheduler picks the next guy to occupy the CPU by the rule that a highest priority ready process is picked. If we follow this heuristic and give this guy a higher priority vis-a-vis these guys, this guy's priority is likely to be larger than these guys, all of these guys. And so this guy, although it's now joining into this group from sleeping or having been blocked, because of its higher priority, it's likely to be picked next to run on the CPU. So when it's ready, it's likely that this guy will soon or almost immediately get the attention of the CPU, thus giving it improved responsiveness, which is what we want this guy to have. And we give it a small time slice because by its nature, it's likely to run a little bit on the CPU, but then again, give up the CPU voluntarily because it's doing blocking system calls. So a small time slice is adequate for this guy. On the other hand, if a process is CPU bound, we want to give it, compared to these guys, a low priority, but a large time slice. Of course, here we might think, oh, but if we give this guy a large time slice, won't that then prevent these IO bound guys from being able to run because this time slice is large? Not so. As we just saw earlier, user mode, kernel mode, and here is a CPU bound guy. So this is a CPU bound guy. It has a low priority compared to these guys, but it has a large time slice. That's the idea. So it's now running, it's current, this guy. And it just keeps using the CPU. That's what this guy is doing. And here is another process, which is IO bound. So this guy is IO bound. But it's been blocking. It's not ready. It's not running. So let's take the sleeping case. It's been sleeping. So it doesn't need the CPU while it sleeps. But after its sleep time has expired, the OS is going to wake this guy up. So this guy now becomes ready. And that is done through the bottom half piece, in this case number 2, as we discussed. So you need to know all these flows. There are not that many flows, but you need to understand how this software behaves in time. That's to understand what this software does. So the clock interrupt handling part, which is the lower half, we know, takes care of waking up, sleeping, and blocked processes, because when a message arrives, who handles the message? Of course, through interrupt the lower half. So therefore, the lower half is going to wake up the sleeping process so that it now becomes ready. And by this guy is going to have a higher priority than this guy. Suppose this guy has priority 20, this guy suppose has priority 40 as an example. This guy has a large time slice. Suppose this guy has a time slice of 100 milliseconds. Whether that's large or not, let's just say this is large. This guy is going to have comparatively a smaller time slice. Suppose it has 50 milliseconds as its time slice. But it has higher priority, this guy has lower priority. But the reason why giving this guy a large time slice does not damage, does not reduce this responsiveness that we want to provide for these IO bound guys is when this IO bound guys now becomes ready. So it now becomes ready. And from that moment, how long will it take until it occupies the CPU? Because that is what determines responsiveness. If we tally that, if we keep track of that, then it will be that through this clock, this guy checks and it makes it ready, and then it calls the scheduler. That's the control flow of number 2. The scheduler runs, the scheduler checks, compared to this guy that just woke up, or in other words, compared to the current guy whose priority is 20. Among all the ready guys, is there a process of equal or higher priority? And now, yes, the answer is this IO bound guys that now has become recently ready has a priority 40 that's strictly bigger than 20 by this rule. So you can look even in Xenu inside the code of RISC-Cache and check that that's what we are going to determine. We are going to pick the front guy in the ready list, which must always be the highest priority guy, and then check its priority against the current process's priority. And here, lo and behold, we find this guy has higher, because that's the rule that we've been trying to follow. How we make this happen, that we will come back to in a second. So that means that this guy is chosen. So this guy we called old in context switching, and we context switch this guy out, and we context switch in this guy so that this guy now becomes current. And so the fact that this guy, that is the CPU bound guy, had a large time slice does not harm, does not hinder this does not hinder these IO bound guys from getting improved responsiveness because of the setting. When they become ready, then through this bottom map path, the scheduler is immediately invoked. And this guy checks and it finds, oh, there is a newly ready IO bound guy that has a higher priority than the current CPU bound guy. So this guy is now going to become the new current guy, and this guy is going to be context switched out almost immediately. Unless the current guy is, of course, an IO bound guy itself. Then it's a competition between those IO bound guys. But when we compare between CPU bound and IO bound, we can see that giving these guys a large time quantum does not diminish the responsiveness that we are trying to provide to these IO bound guys, which are nice processes because inherently they don't use up much CPU. They just voluntarily exit from the CPU because they keep blocking all the time. So this is a perfectly good way of setting the time slice for that reason. And as I noted, when this happens, we say that we are preempting. Preemption. So this IO bound guy preempts the CPU bound guy and runs instead of the CPU bound guy for the reason that we just discussed. And when the IO bound guy has a small time slice, it doesn't really matter that it has a small time slice because if it's an IO bound guy, it's not going to need much it's not going to need much CPU time to begin with. So this is plentiful. That's the idea. And because we gave the CPU bound guys large time slices, if for instance, for some reason, all the ready guys are CPU bound and the current guy is CPU bound. So there are no, suppose, IO bound guys inside the system at this moment. Well then, having responsiveness is not a key requirement of CPU bound guys. It helps them, but it's not a key requirement as in this IO bound guys. So here, reducing the context switching frequency overhead by having a large time slice so that this guy gets to get its full fill by running for 100 milliseconds, then paying for the overhead of context switching, and then making, suppose, this guy current and making this guy run for its full fill, and then switching to this guy and then making it run. So overall, by not having too many context switches going on, because the time slice is large, that's the right way to approach it. You don't want, when your apps, your processes are mostly CPU bound guys, you don't want them to have a small time slice because by definition they all need CPUs. Just getting CPUs is what they need most, not responsiveness. And so therefore having a larger time slice is beneficial for this setting. So overall, this table that is drawn here strikes a reasonable balance, qualitatively speaking, because this says large, small, low, high. What does large mean? What does small mean? Everything has to be, of course, quantified at the end of the day. We're talking about science and engineering. This is not some opinion stuff. This is where everything has to be made concrete, where the rubber meets the road. This is not something abstract. Everything will become numbers. But conceptually, this framework given by this 2x2 table captures the trade-off that we want to achieve between CPU bound guys and IO bound guys so that we are achieving a more sophisticated sense of fairness beyond round robin so that the IO bound guys are additionally imbued with responsiveness. And that's been the general goal. General goal, I say, because this is all true of Unix operating system kernels that schedule Windows. And it's been true for Linux, not the current Linux. There is a Linux scheduler just earlier to that, not that many years. How many years has it been now? I'll not even speculate, but in the order of 10 years maybe, plus minus. But that scheduler that Linux then used was a constant time scheduler. So it's a constant overhead scheduler. It is very similar to the scheduler that you're implementing in Lab 3, which is also similar to those implemented in Unix and Windows. So the one that you're implementing in Lab 3 is sort of one that has different aspects of these modern schedulers. But this earlier scheduler of Windows did differ in one respect from those of Unix, Windows, etc. And there are, of course, different versions of Unix, so there's not one Unix, but I'm just loosely, roughly talking about the overall shape of things. In the earlier constant overhead Linux scheduler, this was actually reversed. So these IO bound guys were actually given a large time slice. What would be the justification for giving these guys a large time slice? Well, on the surface, we might say, well, it doesn't hurt because, okay, we give this guy a high priority and a large time slice, but this guy is not going to use up much time to begin with, so what's the harm in giving this guy a large time slice? So one could see that that kind of reasoning seems to make sense, but it's not quite that, because if you dig a little bit deeper, then we will here realize that it's easier said than done to say that a process is IO bound or a process is CPU bound. Processes in the real world, they don't arrive saying, hey, I am IO bound, I am CPU bound. There is no such thing. The operating system, this guy, the kernel, must somehow figure out if a process that's being forked, that's being created, is this way or that way or hybrid, whatever the case may be. So this is not a given. All of this stuff is under the assumption that if we knew this were to be the case, then what would be the strategy? What would be the method that we want to follow to achieve a superior fairness that is in keeping with the special properties of the workload, which comprises processes running under operating systems? To achieve that, this table would make sense. However, this is uncertain. We can do our best and we'll see how to do it. We can say that a process is IO bound, but we cannot be sure. It's something that we classify, that we determine from a process's behavior, but its behavior may change in the future. So, going back to this, if in this table this is not made small but large, and this guy is IO bound, it wouldn't make a difference because it wouldn't be using up much CPU. But suppose that you didn't classify this guy correctly, or this guy was IO bound, but suddenly it changes its behavior to being CPU bound. What can then happen? If that were to happen, which can of course happen in real life, then you have an IO bound guy which has high priority and on top of that a large time slice, which means that when this guy is running and other processes are trying to run, they may not be able to run because their priorities may be smaller than this guy. But not only that, this guy has now a large time slice. So it's going to monopolize the CPU for some time window. And during that time window, other processes may not be able to get the CPU, and that's not a good thing. So for all of these subtle reasons, the basic rule, which is low priority for CPU bound, high for IO bound, large time slice for CPU bound, but comparatively small time slice for IO bound, that has worked well, and it's the approach that most modern production kernels are still following. But as I noted historically, the previous Linux scheduler did not. But instead of changing this to be large and small, What Linux did as a community is they just scrapped the old scheduler altogether that followed this policy, and they came up with a completely new scheduler called CFS. And CFS stands for Completely Fair Scheduler. And I'll talk about what that is after we are done discussing this matter. So keep this table in mind. What is the underlying rationale for doing that, and how it fits into scheduling with the peculiarities, with the idiosyncrasies of the workload that processes that need to run on CPUs managed by operating systems look like. So we always have to make sure that we don't just dream up things that don't match reality. We always, in science and engineering, have to look at reality. What does reality look like? And then make scheduling fit, match the reality so that the scheduler can do a good job. To not know what your workload looks like and then just dream up something, that's highly likely to lead to bad results, obviously. So in computer science, as is the case in most good engineering and science in general, you always have to look at, you have to measure what's going on. And that's going to be the basis on which then you can come up with good solutions. If you do not measure, then it means you don't know what's going on. And if you don't know what's going on, all that you can do is guess, speculate, have some educated guesses if you're particularly sort of intuitive kind, but it's not a winning strategy. Good science, good engineering is always invariably based on measurement. And so in the labs, you are going to measure this or that so that you know the numbers, and the numbers tell the accurate full story. And luckily in science and engineering, we're able to measure. We don't have to speculate. That's the huge strength that we have. So keep in mind that when you're measuring things in the labs, it's done for the benefit of making us be able to do things better than if we did not have these measurements. So now let's look at one specific example of how this table is realized in a very sophisticated operating system when it schedules processes. And that example is that of a variant of Unix called Solaris. So this is what is historically known as a System 5 variant of Unix. Why System 5? All of this historical stuff is interesting but not relevant at this level. I don't care whether you know the history too well or not. These are just coffee chat. What you want to know is you want to know the content of what is this guy about. In computer science department here at Purdue, till recently, we ran our servers mostly governed by Unix Solaris. It is because this was a super reliable, it was an industrial grade operating system. So when other systems crashed and they did bad things, this guy was super reliable. It was one of the top most reliable and efficient Unixes that were used in industry and universities. So we ran this thing for decades until recently, where Linux has made so many strides, because when Linux came along at first, it was really just a toy. We ran it here or there, etc. But well, it was just a variant of Unix. It was open source, great, and all that stuff, but there was nothing special about it. It crashed all the time. It was not a reliable operating system. But much time has passed, and what's remarkable is that this open source operating system, with thousands of people working together to improve and build this code, managed to build a very reliable system, a very reliable OS. And that was not predictable, because this has nothing to do with sort of engineering or science. it's sort of a social phenomenon that you could have this group of thousands of developers all across the world somehow being able to work in a meaningful way together, with, of course, a strong influence by the guy who came up with this OS to begin with, so that we can now benefit from it. It's a major, major accomplishment, not so much at a technical level. Well, it is technically interesting, but it's nothing special per se. But the social sort of dimension of being able to accomplish that, that's really amazing feat. But we have this guy now. And so in CS, we have thus recently switched from Unix Solaris to Linux, and I think wisely so, because Linux is a super high-end now, very reliable operating system. But let me here talk about how scheduling was done in Unix Solaris, and we used that all the time because it was a very high-grade operating system. And this Solaris operating system followed this table that I just discussed, and we are now going to make this qualitative CPU bound, IO bound, priority, and then time slice. And this was low, this was high, this was large, this was small. That's the table that captured things. Again, Linux, the older Linux, had this thing reversed. But let's not talk about that. We're talking about Solaris. So how did Solaris implement this policy of giving higher priority to IO-bound processes vis-a-vis CPU-bound guys, and then give them smaller time slice vis-a-vis CPU-bound guys? How did it actually look like? What happened? So to do that, let's rid of this guy and look at a table. This table is on our course website. You'll see the bullets there under the topics covered. And this is the scheduling table that by default would be shipped with Unix Solaris if you had a computer that was running Unix Solaris. So this would be a default table. It can be modified, it can be configured differently, but this would be the generic table that Solaris would then advocate being used by servers, by desktops, by PCs as being a reasonable thing to do. So in Solaris Unix, it uses 60 priority levels. So it uses 60 priority levels or values to schedule processes. And these processes are called TS, time share processes. There are also real-time processes that have a higher priority than these guys, but we are not going to discuss them here. So these priority levels, counting at 0, that's the lowest guy, number 1, 2, 3, and 59. So there are 60 priority levels. A process is created, suppose forked. It gets some default initial priority. Just to keep it simple, suppose we give it priority 20. So we fork a process, and just to explain things clearly, suppose that we give it a priority of 20. So it starts its life, a process with PID, suppose 20,000 is born, and we give it a priority of 20. But this is only its initial priority. And based upon this priority, it has to compete with all other ready processes. Again, the same as in Xeno. So there's all other ready processes. A1 with a highest priority gets to run next. That's the same idea. And suppose this has priority 20. And now this process, suppose, becomes current because among all the other ready guys, 20 happens to be the highest priority. So now this guy has become current. It runs. The kernel tries to observe, what is this guy doing? Is this guy behaving in a manner that looks like it's CPU bound? Or is it behaving in a manner that looks like it's IO bound? But you don't want to do this by spending a whole lot of cycles, because everything that the OS does that's not a direct request by the by the user process, is overhead. Keep in mind, we have this utilitarian view of a OS as being a server. It's there to satisfy the needs, the requests of processes. That is its main reason for existence. Nothing else. That's the bottom line. So anything that it does that's not in direct need to accomplish that is something that is not time that is wisely used by the OS. So to spend too much time, for example, using AI techniques or using machine learning to determine, is this guy CPU bound or not, is this guy IO bound or not, it may be more useful, it may give you a better result. But you always have to weigh the benefit against the cost, and the cost is overhead. So even though you may be able to classify them better, if it comes at the cost, at the overhead of having to spend too much CPU time doing this business and not running the instructions of the app process, then it can be viewed as being not the right thing to do. So that's been always the attitude in operating systems, where efficiency and speed is at a premium. So we want to always keep in mind, performance is key. Of course, we need to have correctness. Things must run correctly, but this is necessary but not sufficient. We need to ensure that we have high performance. And this is the environment in which operating systems live. So, going back to this example of Solaris, which is using 60 priority levels that are being assigned to these generic app processes under this class called TS, which is just timeshare processes. By default, we are calling all of our processes timeshare processes. And in this example, a newly born process starts with some initial priority, suppose 20. It now becomes current at some future time, and it's now running. The OS, using low overhead methods, super important, not expensive fancy methods, but low overhead methods, tries to glean, is this guy more IO bound or is this guy more CPU bound? And next time when the scheduler has a chance, if it thinks, oh, this guy is behaving like an IO bound guy, I'm going to bump up its priority, suppose from 20 to 29, okay, let's say 31. It bumps up its priority from 20 to 31. Why? Because its behavior seems to indicate that this guy is an IO bound guy. On the other hand, this guy is running, but it kind of behaves more like a CPU bound guy, not an IO bound guy. Then the OS, that is the scheduler of the OS, next time that it has a chance, does the opposite. It bumps down. It decreases the priority. Suppose it decreases from 20 to 11. So in this case, we say that the priority, that is this process, is being promoted, and here it's being demoted for obvious reasons. So we are decreasing priority, we are increasing priority. So the priority is not fixed anymore. Not fixed. In Xenu, you know that when you create a process and then we provide some priority number like 20 that you used, then in that case, this priority will never change unless you ask the priority to be changed by making a change prior system call that you then turn into a bona fide trap system call in lab 2. But unless such a thing is done, Xenu as an OS is a static priority scheduler. So static meaning priorities do not change. But now we are saying we are going to observe what a process does, and based upon what we observe, we are going to increase or decrease the priority based upon is it behaving more like a CPU bound guy or more like a process that is IO bound. And we have to do it with low overhead. So what is a method by which, using low overhead, we can get some idea of whether a process seems to be CPU bound guy or an IO bound guy? Well, you know the answer already, which is a very direct, intuitive answer, namely a process that's current, so that's now running, that eats up all of its time slice. So it consumes all of its time slice, quantum. So this time slice counting business by the lower half hits zero. Decrement, decrement, decrement. Each time that the clock handler runs, it's at zero. That means that this guy used up all of its time slice, meaning it was running on the CPU a whole lot. So when the OS detects, because the OS is a scheduler in Xenu, reschedule is called by whom? By the clock handler, which is called by whom? By the clock dispatch code, which of course is triggered by a clock interrupt. So we know all of this. So the clock handler checks, did the current process, because here's a current process running, there's a clock interrupt, so asynchronously we run the lower half. This is all lower half code. And the clock handler decrements the time slice in Xenu. The time slice we said is called preempt. This is a global variable. It keeps decrementing, and if it's equal to 0, then it knows, okay, this guy has used up all of its time slice. And so now it calls the scheduler, and the scheduler, well, of course, not in Xenu, because Xenu is a static priority scheduler. But in Unix, Windows, etc., then the scheduler would say, oh, okay, this guy now has eaten up all of its time slice, so it seems to, at least for the moment, behave like a CPU bound guy. So let's demote its priority. On the other hand, it is not this way that the scheduler is called. This was pathway 2 prime, as you recall, as we called it. Suppose the current guy is running, and in Xenu, suppose it makes a sleep MS system call, which is a blocking call. It says, I want to sleep for 2 seconds. So here it's voluntarily giving up the CPU by wanting to sleep for this long period of time or short period of time. It doesn't matter. Of course, sleepms is a system call, so the upper half of the kernel is responsible for handling that. And in our picture that you are now getting, I hope, very familiar with, so user mode, kernel mode, this is our current process that's making a sleepms system call. So we are trapping from user mode to kernel mode, and it's the upper half of the kernel that handles, of course, the sleepms. And then sleepms, of course, calls the scheduler, which is wedged in between. So it's now this guy who also calls the scheduler. And the scheduler notices, this guy hasn't eaten up all of its time slice, but it makes a sleepms call. In general, it's making a blocking call, like read, like sleep, etc. So it's voluntarily giving up the CPU. And that's an indicator that this process seems to be IO bound. So the scheduler says, let's promote this guy's priority from the current value to a higher value. This is the most simple and direct heuristic that kernels use to try to gauge if the current process that's running is behaving more like a CPU-bound guy or more like a IO-bound guy. And if a process changes its nature over time, then it will, for example, it was previously IO bound, but then later on it changes to just hogging the CPU. Then it's going to make less blocking calls. It's going to more encounter having all of its time slice being consumed. That will lead to demotion, demotion, demotion of the priority. Or a process was earlier CPU bound, so it kept using up all of its time slice, but then it changed its nature and it's now becoming IO bound. So it's making blocking system calls more. So let's use sleep as our representative example. The kernel notices that. It bumps up, it promotes the priority, it increases it. So therefore this guy, the more IO bound it behaves by making blocking calls, the more its priority will keep increasing. And this is exactly the method that is employed by Unix Solaris. And I discuss Unix Solaris to show in a quantifiable way how the table is actually implemented, because it's the cleanest, in my view, and the most elegant way of making that table work. The other versions of Unisys and Windows, etc., they do the same thing in terms of the qualitative actions. But the formula and the equations being used are much more messy. This way of doing it is clearer, so it's also much easier to discuss. And so this is what we will now look at to see how in one setting scheduling is actually being carried out. And here to augment, when a process seems to behave like it is IO bound, we are of course going to increase its priority from before, but we are going to decrease the time slice. So keep in mind, when we increase the priority because it seems to be behaving like an IO bound guy, then yes, we increase its priority. But at the same time, we decrease its time slice. So it's not only the priority that is changing, the time slice is also changing. So neither priority nor time slice are constant. They are dynamically changing over time. So a process may be born with this priority and that time slice. But over the course of its lifetime, those values will keep changing in order to achieve the goal that we just discussed earlier. And so let's now look at the table that I showed earlier and what it means. So here are the priority levels. This is the last column here. So priority level 0 till 59, because there are 60 priority levels. This is low priority, this is high priority, important, less important. And just to stick with the example, a process has been created, suppose using fork, and it starts, suppose, at priority 20. So how to read this table? It's a kernel table. It's a kernel data structure, just shown as a text file here. So it starts with a priority value of 20 when it is created. What is its time slice? Just follow this row until we hit the first column, which is tagged timeshare, which is the process class that we are trying to schedule. They all fall under timeshare, unless you are in what is called system processes or real-time processes. That's another matter. Has no relevance here in what we are discussing. But this is the key thing, quantum time slice. So if you start off your life with priority 20, it says that you get an initial time slice of 120 milliseconds. So that's what you get. So you start your journey, your life, as a process with priority 20 and time slice 120. Suppose this process, now become current because you are the highest priority process next and you are context switched in. And suppose that you keep hogging the CPU and you eat up all of the time slice that you are given. So you are spending 120 milliseconds and now it's down to 0. What happens to you next? We said that the reasoning is, oh, this guy behaves like a CPU bound guy because it did not block, it did not voluntarily give up the CPU before expanding all of its time budget, this 120 milliseconds. So what should happen next? Its priority should be demoted, but by how much? This is what the table will tell you. It says, look at this column, TS, time quantum expired. This is this guy. It used up all of its quantum, its time slice. So this is row 20. I keep losing here the track. So yeah. So this is this row. So this guy was our row. And this guy says, oh, if you have been detected to have spent all of your time slice, you get demoted in terms of priority and your priority becomes next 10. So it starts its life with priority 20. But because it spent all of its time slice, because this guy reached 0 by decrementing by the lower half of the kernel which handles the clock interrupts, the priority now changes from 20 to 10. Demotion. Demoted. So next time that this guy runs at priority 10, where are we? We are right here. That's our new priority. So this is this guy. So if it runs next, it runs with priority 10. So because it's new priority 10, when it has to compete with all the other ready guys for the CPU's attention, it is in a less advantageous state than before, because before it competed with 20 as its priority, but its new priority is 10. So therefore, it is less likely to get picked to run on the CPU. But at 10, what is its new time slice? Go up the row. Its time slice is 160. So the time slice has increased from 120 to 160. So although the priority has decreased from 20 to 10, the time slice has increased because this guy is deemed to be more CPU bound by the fact that it used up its time slice. Now the opposite way. So again, we start off live with this process with priority 20 as our initial priority, and our time slice is 120 milliseconds. These are all in units of milliseconds. This guy now becomes current. It runs on the CPU. But before spending all of its time slice, suppose it has 80 milliseconds still left. Let me use a different color. So suppose it's running and it has spent only 40 milliseconds. So 80 milliseconds is still left. At that moment, it makes a blocking system called like sleep, like read. And read blocks because the information to read is not there yet. So before it spends all of its time slice, it makes a blocking system called like sleep, like read, and it actually blocks. So the OS notices that because the upper half calls the scheduler, which is wedged in between. And then the upper half notices, oh, this guy is blocking voluntarily. Why is it blocking voluntarily? Because it's blocking by making a system call. And it has not used up all of its time slice here. There's still a lot of time left. So this guy deserves promotion because this guy is behaving in a manner in which it seems to be IO bound and not using up much CPU because it only used up 40 milliseconds, not the full 120. So We're going to promote this guy's priority from 20 to what value? Look at the third column. TS, sleep ret, sleep return. So here inside the kernel, the term sleep is used internally. Even though this might be reading and blocking, it doesn't matter. It's internally speaking equivalent to sleeping. So it's a good term to use internally. But the point is, this column says what should happen to the priority of this process when it blocks without having used up all of its time slice. And what is the number here? 52. It gets a huge bump in priority, that is a promotion, from 20 till 52. Where is 52? Let's see. Here is 52. And we lost it because 20 is right here. So 20 is here. And now we are promoting the priority. How do I know? Because this is what it says. It says 52. I think I highlighted the wrong one. Here is 52. So we are going here to 52. That is its new priority. And at 52, when it's competing with other ready processes, it's of course highly likely to get picked because its priority is pretty high. The highest priority is only 5.9, and there are many priorities below it. And at 52, what is its new time slice? We go left of the row and see, oh, its time slice, its new time slice is 40 milliseconds. So this shows that, oh, its priority has been increased. It's been promoted, but because it has been deemed to be I/O bound. Why? Because it blocked without using up all of its CPU time, which is its time slice. So it jumped from 20 all the way to 5.2. And then next time it competes with this priority, with this much higher priority, which makes it highly likely that it's going to be picked next or soon, which increases its responsiveness. That's great. And its time slice is now reduced from 120 to 40. So it goes in the opposite direction, following the table that I described earlier. This is it. That's the entire table. Now you may see that there are these two other columns, and I would discuss these two other columns if your lab 3 assignment was to implement this policy of Solaris. In some semesters, that's what I give out as the problem to solve. Implement a version of Unix Solaris, this guy. And there I explain what this additional information is. For our discussion, where in your lab 3 you are not implementing this version of scheduling, we are going to skip that because it's not essential. It's an optimization that's useful to know, but in this context, it's not key. So just ignore this and focus on what we just discussed as a concrete quantitative method that realizes the 2x2 table that we just discussed earlier. So what remains in scheduling is to just talk about how the current Linux scheduler does scheduling, which is slightly different, not better, but slightly different. And that will wrap up our discussion of scheduling as far as modern operating systems are concerned. So we'll continue from here next time.